Colton here from Modern Robotics. We're going to make a wall-following robot using one optical distance sensor and a two-wheeled robot. Those three things only. And then we're going to make a robot that follows a wall just like this one is. If you move it farther away from the wall, it'll correct by driving closer in. If you move it closer to the wall, it's going to correct by moving farther out, and it'll keep this nice straight path down that wall using the readings from the optical distance sensor. So let's begin. I'm going to go into my up modes, and I'm going to say new Java class. I'm going to name my Java class MRI ODS wall follow video. I'm sure you can come up with a better name for that class. That's the naming convention that we're sticking to. I highly suggest that your team picks a naming convention and sticks with that name convention. So here inside of my class, we're going to first make a optical distance sensor. We're going to say optical distance sensor, and notice how since I selected that from the drop-down list, it imported optical distance sensor automatically. So I'm going to say optical distance sensor. I'm going to call this one ODS. Then we're going to import the motor. So I'm going to say DC motor. You can see here on this list, if I click enter, automatically imported DC motor. I'm going to call one of my motors M left. M in my program stands for motor, left motor. DC motor M right. Hope that was predictable. Moving down here, I'm going to have the raw reading from the optical distance sensor, and then we're also going to have a linear reading. So both of those, one is me an int, and the other one is going to be a double because the linear reading is going to have decimal places. I'm not putting any comments in this code, but the example program I publish will have comments in the code. So if you get stuck, well, what is that thing? You can go through the example program that we'll have for download, and you'll see comments in there. Remember to comment your code with as they're going along to remember what these things are. If you haven't seen the optical distance sensor general video yet, we'll show it right here. Be sure to check that out. That's going to talk about why we're using the linear reading instead of the raw reading. And we're using the linear reading in this video so that as we move closer to the wall, the value changes in a linear fashion instead of an exponential fashion. You'll understand a lot more, though, if you go check out this video about the optical distance sensor in general. We're going to move forwards into our run op mode loop. So I'm going to say override So this is our run op mode program, and then our main loop is going to be inside there. So this is where our initialization takes place. We're going to start out in initialization by saying that the optical distance sensor is hardware map. It's not importing hardware map for me like I would like it to. So to get around that, I'm going to have to manually type in the import that we need for the hardware map. And that import is event loop dot op mode dot linear op mode. Import helps if you spell things correctly. Import. There we go. And then down here, when I say hardware map, okay, guys, you're probably thinking, Colton, your mistake's right there. This is why it's not working. This is why. Okay, up here, our public class needs to extend linear op mode. Now down here, hardware map dot DC motor. Oops, we're going to do the optical distance sensor first. This is a optical distance sensor, and we're going to get that. We're going to call it ODS. Why are we calling it ODS? Because it's all lowercase letters. Lowercase letters are the default keypad you get on your touchscreen, so we want to use all lowercase letters. We're going to do the same thing with M left is hardware map dot DC motor dot get, and this one we're going to call ML for M left. Again, all lowercase letters. And it describes this guy. It doesn't describe the port it's on because you can put it on any port. It should describe this instance right here. We're going to do the same thing with M right. Excellent. Next, we're going to reverse M right, and now the robot that we designed this for has gears on the left and right side. It has 2 gears, so 1 gear on the motor, 1 gear on the wheel. That makes it reversed from what you may have. If you have the motor connected directly to the wheel, you'd have to reverse the left wheel instead of the right wheel. So here we have M right set direction. And this is not, oops, I need my dot operator. Silly Colton. Set direction is going to be DC motor controller, and notice how automatically up here it's going to import DC motor controller. If it doesn't do that, you'll have to type it out. And this is going to be dot direction DC motor controller. Oops, it's just DC motor. Dot direction dot reverse. So it turns out we really didn't need that. Oh yes, we will. We will. Down here, we're going to use run using encoders for both of these. This way we have a more consistent speed. Depending on the battery level, the speed may change. But if we're using run using encoders, the speed is going to be constant regardless of what our battery level is. For this, you would need encoders on both motors. Run using encoders. Now this, I think this is important enough for a comment in the video. This is setting motor to run at constant speed, because that's what it truly is in the specification for the motor controller. It's actually called run at constant speed, but in here it's called run using encoders. A little confusing, but we can match those up. We're going to do the same thing. I'm just going to copy that and do the same thing for left. Wonderful. Next, we're going to wait for the start button to be pressed, and then we will continue in a loop while op mode is active. While the op mode is active, we want to first get the new optical distance sensor reading. So we're going to say ODS reading raw equals ODS dot get light detected raw. We want the raw value because it's between 0 and 1023, and that's the more common thing. So once you move across platforms, it'll be more familiar to use the 10-bit value instead of the decimal value. That's actually what's coming back from the controller. So you get the actual accuracy instead of 0 to 1. And then the next thing we're going to do is we're going to calculate ODS linear. ODS linear is going to be the raw reading to the power of negative 0.5. So we're going to say math.pow. I think that's one of my favorite functions just because it's pow. Raw value to the negative 0.5. Correct? Correct. Next, we aren't going to set our motor powers yet because we don't know what the values of optical distance sensor are. So we're going to leave it at this for right now. But right here is where we'll set our motor powers. The next thing we're going to do is set up our telemetry data. So our telemetry is, we're going to add in some lines there. Our first line, and we're putting numbers first so that they come out in that exact order. We're going to say what our ODS linear is, and that's just this variable here. The last thing we'll do is wait 1 full hardware cycle. Now, right here, you're going to download this program to your robot. And from there, you're going to start the program and read this value on your driver station, the ODS linear value. And you'll want to read it when the robot is as close as you want to get it to the wall, and then also when it's as far as you want to get it away from the wall. Usually we'll use an equation of y equals mx plus b, but in this case, the readings just came out to be so gosh darn perfect. So we had our robot close to the wall, and what we wanted to do was find the value when we were close, when we were at the center, and when the robot was just too far away. And we're going to do this using the ODS linear value. So we did that using that breaking point in the middle of that program where we paused there, and we found that when we were too close, the ODS value linear was 0.05. When we were just right, the Goldilocks zone was 0.14. And when we were too far away, it was 0.25, which is good. It's linear like we would expect it to be. Now the next thing we want to do was to visualize what's going to happen. So the optical distance sensor is on the left side of the robot, so that means if we're too close, we need to speed up the left motor and slow down the right motor. So we're going to look at M left and M right. So if we're too close, we need to speed up the left motor. We want to go at maximum speed at about 0.5, so let's say 0.5. And if we're too close, we need to slow down the right motor. So I'll go about 0, just say 0 completely. If we're center, Goldilocks zone, we're going to be going about halfway between there, so let's say 0.25 for both motors. If we're too far away, we want to be going the opposite of this. So we're going to be going 0 and 0.5. Now it turns out that if we multiply the ODS linear reading by 2, we get the right reading, or the right power we want to use. 0.25 times 2 is 0.5. We're going to round this to 0. Times 2 is still 0. If we then take that, if we take 0.5 minus that value, so 0.5 minus 0 is 0.5, 0 minus, or 0.5 minus 0.5 is 0, that gives us M left. So take this, put in your robot, see what you get on your wall. It may be different. What you can do is actually take the values here and use them in y equals mx plus b to get an actual equation that scales from when you're close to when you're far, using the powers when you're close. I found that with the values that I had, with the powers I wanted to use, it ended up working really beautifully if I rounded the 0.05 to be just 0. So what we were able to do is just say M right set power to be ODS linear times 2, because it's ranging between 0 and 0.25. I really want a range between 0 and 0.5. And then the other one, M left, I want to set the power to be 0.5 minus ODS reading linear times 2, because I want M left to be the opposite of what M right is. Not opposite as in put a negative sign in front of it, but the opposite as far as where it is between 0 and 0.5. That way it's always moving forwards, but the values will be changed so that if our value is right in the middle, so when I was too close, the value of the ODS linear was 0.05, which I'm rounding to 0. And when I was too far away, the value was 0.25. So right in the middle is 0.12. And when I have that, the readings are the same. So both the right power and the left power will be 0.25. So when it's perfectly in the middle, when you got the Goldilocks state, you're not too close, not too far away, the robot's going to be going straight because both motors are going to be using power of 0.25. And then as you deviate from that, the motor power will change proportionately to how far the linear value is changing. So that's how we came up with the equations in the video we just had, but that was way too simple. So let's say the values did not line up like this, that we had this times 2 equals this one. So let's say instead, we'll bring in a new piece of paper. We'll say we had, we're just going to stick with close and far, and we have ODS linear, and then we also have our M left and our M right. And the way we want to turn still doesn't change. So if we are on the close side, we still want to go 0.5 and 0. If we're on the far side, we'll still want to go 0 and 0.5. But let's say that our ODS linear values were not as simple as they were last time. Let's say that they were, let's say 0.3 and 0.6. So the hard part about this is that this isn't 0. We can't just say, whoa, this times something number is going to be this one. So what we're going to do with this is use y equals mx plus b. Yes, that formula you had in middle school that you're never going to use ever in life, you're going to use that in life. So we're using the formula y equals mx plus b. And the y value is our output. The x value is our input. Our input is ODS linear. The output is m left or m right. So we're really going to have two of these equations. We'll have y1 equals mx plus b and y2 equals mx plus b. Now let's rewrite this one more time so we can say that, or we'll cross these over. So we'll say that m left is y1, m right is y2, and we'll say ODS linear is x. So we have two equations here, x, y1, y2, x, y1, y2. And to get this equation, all we need is 2 points. And then we can get this linear equation. That's why we're using the linear value here. So our 2 points for y1, we'll say that, we'll do this for, let's say that this is m left, and over here we'll have m right. So for m left, we have 2 points. We have two x values, 0.3 and 0.6. We're going to use those in both of these equations. We have 0.3, 0.6. Both of these are m left. So 0.3 with m left is 0.5 as the y value, the output. And 0 over here. For m right, we have still 0.3 and 0.6. Now the difference is that now for m right we have 0 and 0.5. So the opposite way around. So from there, I'm not the one to teach you how to use y equals mx plus b, but from there you can get two equations down here as far as m right equals, you'll have a numeric value for m, x, which is your ODS value, you'll input that into the equation, plus a constant b. Same thing for m left, and then you can use that in your program in place of where we had ODS times 2. So really, for the program that we had, m was 2 because we took ODS times 2, and for one of the values, for one of the motors, b was 0, and for the other one, b was negative 0.5, or excuse me, m was negative, and then b was 0.5. So took 0.5 minus that stuff. And for that one, it was so simple we could figure out in our head. But if it's not simple, as far as if this value is not 0, then you'll have to go through the process of calculating y equals mx plus b, both your left motor and your right motor, and then it's really beautiful and elegant the way that the robot can follow lines or follow walls. So the same thing can be used in line following. That's how you can make a wall following robot. If you like this video, please be sure to subscribe to Modern Robotics on YouTube and follow us on Twitter. That way you'll get updates when new videos are released or we have new products, etc.